wave rectifier, which is a basic but very significant circuit in electronics, which is used for AC to DC conversion. In this video, we would be looking into simulation of full wave rectifier by means of Simulink, and we would also perform a Fourier series analysis. This includes finding the coefficients of Fourier series, that is mathematically. A very important book dealing with the full wave rectifier is Power Electronics by Daniel W. Hart, and this book is recommended by a number of well-known researchers in the field of power electronics. So specifically, we are interested in chapter 4 with the details of full wave rectifier on page 111. So you can find the technical details over there, but right now we are interested in this circuit, which is figure 4.1 in this book, and over here we have a voltage source, then 4 diodes in a bridge, and then we have a resistor. Figure A is equivalently represented in a simple form, which is over here. Again, we have the same circuit, voltage source, the 4 diodes, and then a resistor. And we are interested in the output voltage across a resistor. So over here at the voltage source, we have this waveform, which is a pure sinusoid, sine function, and at the output we have absolute of that sine function, that is the lower lobes are moved up. So for stable DC supply we would be using filters that would include storage elements like inductors and capacitors, but that is beyond the scope of this video. So we would restrict ourselves to simulating this and getting this waveform by means of Simulink. So as a first step, let us open the Simulink from Matlab. So this is our Simulink block on which we will be plugging in all the circuit elements that are given in this circuit diagram. So let us start with plugging the diodes. So we can go to the library browser. In that we select diodes and we select this diode and pull it over here on the main panel. Let us arrange this by rotating it counterclockwise, and we need 4 of them, so we can copy this 4 times by Ctrl C and Ctrl V. Now this terminal has to be connected with the upper diode in series, and the upper ends of the diode are connected as follows. So next we need a voltage source. Now from the power library, this AC voltage source is plugged to the main panel. So we can configure the AC voltage source by setting the peak value to 320 volts, and we can set the frequency to 50 Hz. Next you will note that this AC voltage source, the upper end, the positive terminal, is connected to the first column of diodes and the lower end is connected to the second column of diodes. So we can connect this to the first column of diodes and the second one to the second column of diodes. Next we need a resistor, and for that in the library browser we can search for series RLC branch, and we can plug this block to the module. Say resistance is simply 1 ohm. Let's double click this and set the branch type to simply resistor R. Again we can make it vertical by the counterclockwise rotation. And this is connected to the upper end terminal and the other end is connected to the lower end terminal. So next we need one ground to connect with this circuit, and for that we are going to select this ground. So this is our voltage source Vs and this is V out, as mentioned over here, Vs and V out. So in order to measure that, we have to plug in two voltage measurement devices. Again, from the library browser, we can search for voltage measurement, and we can bring this block over here, and then we can connect the positive terminal to the upper branch and the negative to the lower end of the resistor to find the voltage across the resistor R. We are also interested in mapping the voltage at the source, so we'll copy this block and also implement it over here. So the positive terminal can link with this branch and the negative terminal would link with this branch. So this is the measurement of the voltage at the source, and this is the measurement of the potential difference across the resistor. And next, from the library browser, we can find a scope, and this scope would serve as an oscilloscope and the measuring device. We can connect the upper terminal and then the lower terminal to that scope. Now all of this simulation comes under the domain of Power GUI, Power Graphical User Interface. So we can select that and pull it over here. So this is our Power GUI. And now let us simulate this for say 0.1 second. Now for better visualization, we can go to the properties, and then in the main we have number of input ports. We have two input ports, one for the voltage source and another one for the output voltage across the resistor. So in the layout we can have two rows, and let us apply that. So therefore at the voltage source we are having the AC voltage, and across the resistor we have a full wave rectified signal where this part is basically flipped upward. And this also ensures that the simulation is working fine. The peak voltage is approximately 320 volts for each one of them. So these were the time domain plots, but we would need the spectrum analyzer to display the frequency spectrum of the input signal. So we are interested in the spectrum analysis of the voltage across the resistor. So let us pull this and connect it over here at the output of this measuring device. So if we run this experiment, so we would be given with this error that the spectrum cannot be displayed for continuous or infinite sample times. So this is the bottleneck for spectrum or scope. So what we can do is we can apply a sampler in between so that the spectrum has a sample data, and this can be achieved by using zero order hold. And let us fix the sample interval equal to 1 over 500. We can disconnect this, connect the input of this sampling device or zero order hold to the output of voltage coming across the resistor, and the output of this zero order hold would go to the spectrum analyzer. Now again let us run this experiment. Now the spectrum analyzer says that the spectrum analyzer requires 64 samples to update the display. Run the simulation for longer time to see results. So let us run this simulation for say 10 seconds. So there you have it, the Fourier series coefficients, the RMS values of them. So this is the DC value and the RMS value is approaching 200 for that. Similarly, the first harmonic is at 100 Hz and the value for that is approximately 70, and on the second harmonic the value is going to decrease, and so on. So note that this value is the absolute value of a1, or the first Fourier series coefficient. This is the absolute value of a2. This is a0, or the DC value. So the settings for this plot are as per this criteria. Now let us proceed to the mathematical analysis of the Fourier series coefficients and observe if we can achieve the same Fourier series coefficients mathematically or not. So therefore we have the simulation by means of Simulink, which yields the following results. So over here we have the magnitude spectrum, and for that this represents a0, absolute value of that is the DC value, and the magnitude of the first harmonic, which is a1, or simply the fundamental frequency, and similarly the magnitude of second harmonic. Note that we would have other harmonics, but the amplitudes would be decreasing. This is the double-sided plot of magnitude spectrum. So in the forthcoming video we would be finding the exact expressions and values of these coefficients, that is a1, a2, a0, and so on. That is, we would be performing the Fourier analysis. Similarly, from simulation we have these two plots. The first plot is of voltage source, and you can observe that the time period of this is simply, that is t0 is 0.02. So for the voltage source, if t0 is 0.02, so this would mean that f0 is 50 Hz, which is a simulation parameter that we have already set, and hence omega naught is 2 pi f0, that is 100. But in the voltage across the resistor, that is V output, now the time period has reduced to 0.01. That is, now the time period is simply 0.01. So this would indicate that f0 is 100 Hz. And for this plot, now the omega naught would be 200 pi radians per second. So in order to find the Fourier series coefficients, basically we have to find the kth coefficient by means of this expression, the analysis expression, that is 1 over t0. T0 is the time period for this signal. Integration over a time period t0, which is t0 x of t e minus j kth harmonic omega naught t dt. So we need an expression for x of t, that is this expression. So we are going to get this expression indirectly. So say we have this function again, that is this, but it is now extending to become a full sine wave. The first intercept is as before, which is 0.01, and the second intercept is at 0.02, which is over here. So as in this case, the x of t can be expressed as a sine function which is having 2 pi f0. So f0 is equivalent to 1 over t0, and t0 over here is 0.02. So this is 0.02. So we have 1 over 0.02, 2 pi f0 t, or simply this is sine 100 pi t. So why we are considering this formulation? This is because we are going to limit this sine function in this interval only. That is, we can have the coefficients a.k.a. as 1 over t0, and the t0 for this is 0.01. So this is 0.01, and again this is starting at 0, terminating at 0.01. X of t, we're going to consider this function which is sine 100 pi t, and the projection of x of t on this base, which is simply e minus j k. Now omega naught would come from this part, right? So this was just a workaround, right, which helped us to find x of t in terms of sine function. So this omega naught would be from here, that is we have jk 200 pi t and dt. So this is our reworked analysis expression for this periodic signal. Now let us proceed to solve that. So we know that this sine function can be broken down by means of Euler's identity. That is, the sine theta is 1 by 2 e plus j theta minus e minus j theta. So we would have this coming to 100, that is 1 over 0.01 is 100, and from here we have 2j, there's the j here, again the limit 0 to 0.01, and e 100 pi t j minus e minus j 100 pi t, and both of these exponentials are multiplied with the basis function, that is e minus jk 200 pi t dt. So next we can combine this exponential with this exponential, so we would have 50 by j 0 to 0.01 exponential of j 100 pi t, and since this whole thing is taken as a common, so we would have a 1 here, and from this if you take this function common, so you would be left with minus 2k, and we have a dt here, that is this is our first integration, and similarly we have 0 to 0.01 for the second part. So this formulates our I2. Apologies, there's a minus here, it is coming from here. Now the solution of these integrations, that is I1 and I2, they are very simple, and you would have this argument appearing in the denominator, that is you would have 50 by j, and argument which is simply j 100 by 1 minus 2k, and in the numerator we have the same function which is ej 100 pi t 1 minus 2k with the limits which are 0 to 0.01, and similarly for I2 we have this function now appearing in the denominator, that is you would have a minus j, so this minus and this minus would become plus, so you would have j 100 by 1 plus 2k, and in the numerator you would have e minus j 100 pi t 1 plus 2k. So in the next equality we can take this thing out as a common, so you would have 1 over 2 pi j square and 1 minus 2k plus 1 plus 2k. Now if you set this t equal to 0.01, so we would be left with simply ej pi, so this would cancel with 100, so you would have ej pi and 1 minus 2k, and if you set t equal to 0, so in that case all of this would become 1 because t would become 0. right? So e raised to power 0 is 1, so we would have a minus 1 here. Similarly, from this part we have e to the power minus j pi and 1 plus 2k minus 1. So we can simplify this expression further by using the exponential and its definition, that is we have e j pi 1 minus 2k. So this is equivalent to e j pi times e minus j 2 pi k, and this function from Euler's identity is cos of pi plus j sine of pi. Similarly, this from the Euler's identity is, we would have a cos of this argument which includes a minus, but since cos is an even function, so this minus would disappear, so we would simply have 2 pi k, but for the sine function we would have a minus sign of sine which would be coming out, so we would have j sine of 2 pi k. So they are being multiplied. Now this cos function at pi is minus 1, so this is simply minus 1, and sine function at pi is always 0, so we have a minus 1 coming from here, and this function for all values of k, this is simply 1, so we have a 1 coming out of here. So in short, this function is simply minus 1. Also, e to the power minus j pi 1 plus 2k, so this is also equal to minus 1 for all values of k. Now plugging in this and this function in this equality, so we simply have an ak which is 1 over 2 pi j square minus 2 by 1 minus 2k plus minus 2 over 1 plus 2k. But note that this j square is simply minus 1, so we can equivalently write this as 1 over 2 pi. So this would make this and this positive, that is the j square. So we would have simply, by taking the LCM, 1 minus 2k times 1 plus 2k, and this would be 2 times 1 plus 2k plus 2 times 1 minus 2k. Now this would cancel with this, so eventually we would have 1 over 2 pi 4 by, now this is simple definition of a square minus b square, so this would be simply 1 minus 4k square. So this is our ak. But note that we have missed one thing, which is the amplitude, that is 320. That is x of t has an amplitude of 320. So we have to multiply a 320 over here throughout. So that is, this is simply 320 times 1 by 2. So in the neat form we have 640 by pi 1 over 1 minus 4k square. So this is our ak. Now from here the DC value, that is when n is equal to 0, so this would mean that our a0 is 203.72. Also the absolute value of a0 would remain the same, that is 203.72. For the first harmonic, a1 is minus 67.9 and its absolute value would be positive, that is 67.9. And similarly for the second harmonic, we have a minus 13.58, and for that the a2 is having the positive values. So these are the harmonics. Let us compare them with the spectrum that we obtained using Simulink. So the DC value almost there, 200. This is 67.9 and this is 13.58.